Hello everyone. So we are in the chapter of plastic deformation at high strain rates. So we have discussed about the constitutive relations involving high strain rate problems, and then we also talked about a little bit of dislocation dynamics. So we will continue these discussions today. So that the stress dependence on the dislocation velocity of dislocation velocities has been fitted into different types of equations. So there are different equations. Both empirical and some are of theoretical basis. So for example, Johnson and Gilman have shown that the velocity of dislocation is proportional to the applied stress to the power m and exponential minus e k t. So in this case m is from 15 to 25 if V is measured in centimeter per second and sigma is measured in kg force, per millimeter square. So if it is constant temperature, constant T, so what we can get is V is proportional is equal to k sigma to the power m. So similarly we will write another relation. So there are several relation can be found of the dependence of dislocation velocity on stress. So for example, Rod and Pitt relation is little longer and little complex looking. So this is kT by h capital exponential minus delta h small k, the Boltzmann constant, and then exponential b tau a tau I divided by kT. So this relation here, h is the Planck's constant, so this should be Planck's constant. K is a numerical constant. This k is a, I will write here itself, it is a numerical constant, and then small k is the Boltzmann constant, and B is activation volume, and similarly delta H is enthalpy of activation, tau A is applied resolved shear stress, and tau 1 the long range internal stress. So we don't write or probably discuss details about this equation, so because we don't need it. So or if you are interested more, so you can study the Mark Mayer's book, the textbook. So just to show you that these are some kind of the relation exists between dislocation velocity and applied stress. So just to show you the type of what type of relations they are. So please refer to the book if you are more interested in it. For several other relations are available in the literature, and these relations are for different materials, like Grieman et al. Discussed about copper, and similarly for zinc by Pope et al., Pope and co-workers, and for aluminum Gorman and co-workers fit the curve or fit some relationship with aluminum and lead data. So however, Gilman described the behavior of almost any materials. So that is, velocity of the dislocation is equal to Vs star. So they are the limiting velocity, I will let you know. So this is 1 minus E minus tau s plus V star d e to the power minus d tau. So this is these exponential terms. So here tau is the, as you know, that resolves shear stress. So this tau, so I would write better applied resolves shear stress, and then d is the characteristic drag stress. So it is called characteristic drag stress, and similarly S is also a constant. So what happens is that if the applied stress is very high, it tends to infinity. So V is equal to Vs. So Vs star and Vd star. So that means there is a upper limit of velocity. So these values will not go higher than this, even if you are increase the stress more. So there are different mathematical equations used to describe the dynamic behavior of the dislocations that can be a little confusing. So different mathematical equations to describe the applied stress dependence of dislocation velocity. So that may create some confusion in our mind, but we will see some of the behavior from which is from a plot which is compiled in this Mark Mayer's book. So that plot is nothing but a log plot of plot of resolved shear stress. I will write RSS for resolved shear stress, which is in megapascal, and resolved shear stress is, I discussed this in our materials science basics class. So resolved shear stress that is resolved on the slip plane, whether dislocations on which planes the dislocation move, and then here we have dislocation velocity V in units of meter per second. So what happens here, if you see the scale will look something like this, 10 to the power minus 1 10 square. So if you see this will be very approximate, you for a proper plot, you check the textbook. So I will just draw very very rough plot here that may not be equal to the real one. So sorry, this will be kind of a straight line for nickel, something like this, and then let us say for molybdenum it looks something like this. It's a molybdenum, it's very close to this is kind of a straight line, and then zinc will be something like this. Sodium chloride will be like this, and little sodium chloride will look something like this, NaCl. Then lead will be something like this, Pb, lead will be something like this, and then aluminum comes here, aluminum, even copper is also somewhere close. So these are the plots that shows the dislocation velocity depends on the resolved shear stress. So this from these curves we can come to a conclusion that the slope of these plots, slope decreases as velocity increases. So this is actually not very clear in this plot probably, because this is the log plot. So but this is the conclusion they come to that conclusion, that the slope will decrease as the velocity will increase. If you see that some of the materials for these, let us say we told about some equations, the rod and pit equation, this equation, although it looks complex, but the same data can be fit into a simpler equation like this also. So if you these experimental results of the rod and pit can be fit to this equation as well, this will also be give some approximation. So different equations, mathematical equations, mathematical relations are proposed, but the overall trend you can see from here, this plot, this was compiled from different references, and I think that's they have even published in the Mark Me as an K.K. Chawla's book, metallurgy, mechanical metallurgy. So this is the trend, and then we can draw a hypothetical applied stress versus dislocation velocity. This is they have drawn it for nickel. How it looks like is, so this is the resolved shear stress in megapascal, and this is the dislocation velocity in meter per second. So what happened is, if you see for nickel, so I will not write the scale here, so maybe we can write the straight line behavior. So it looks something like this. So I think this point will be probably somewhere in between 10 to the power 0 to, let us say, 10 square, and then this point is somewhere probably in between 10 0 10, and this point is probably somewhere above 10 square. So now there are three phases, three regions. You can see that region 1, okay, region 1 and region 2 and then region 3. If you check the earlier equation, if it is earlier equation, one of the earlier equations, V equal to K sigma to the power m. So in here. So if you use these relations, so here actually for the first region, so m is equal to m is greater than 1, and here m is equal to 1, and then here m is smaller than 1. So if you use this relation, so you can have the coefficients of m like this, and there will be a limiting velocity, by the way, this limiting velocity. So that limiting velocity is your shear wave velocity, shear wave, actually elastic shear wave velocity, shear wave velocity at 10 gigapascal. So what happened is, because this dislocation, this is all about dislocation dynamics we are talking about, the dislocations, whether it is a screw dislocation or edge dislocation, they generate shear stress and also shear strain. So these shear stress, so the shear stress disturbance, the shear stress, if you consider them as the disturbance, that means we are talking about the wave propagation, so cannot produce velocities higher than the V elastic shear. So here, you know what we talked about, V elastic shear, shear wave velocity, elastic shear wave velocity. So I would write like this. So this so what happens is that, so dislocation cannot move faster than this. So this means dislocations cannot move faster than V elastic shear. So the velocity should be less than that. Now coming to these three regions, so what happens, why this for the nickel alloy? So this, as I told you, this is for nickel. So for this material, why this is like a hypothetical one, but this although it is hypothetical, but the trend is similar. So what happened is, these three regions represent three different mechanisms of plastic deformation. So that is number one, is thermally activated. So I would write here three different mechanisms of plastic deformation. So I would write region 1, that means this region, okay, and then that gives us, this is thermally activated, dislocation motion. Then region 2, that is that mechanism is called phonon drag. We will discuss about that, phonon drag. And then region 3 is the relativistic effects. So we will discuss all three mechanisms: the thermally activated dislocation motion, thermally activated dislocation motions. So dislocations continuously encounters obstacles. So dislocation needs to cross those obstacles to continue the plastic deformation. So you will see what are the obstacles encountered by dislocations. Okay, so we will see the first category is like other dislocations. Other dislocations, that means dislocations interact with dislocation, and then solute atom. We have discussed about that in the material science basics basic class, that lecture. So what we discussed is we discussed that dislocation interstitial and substitutional impurity or solid atoms. So what we discussed are different crystal defects and also strengthening mechanism. So where we discussed that the dislocations encounter some obstacles, and that way the material got get strengthened. So and then vacancies, then small angle grain boundary, I will write GB for grain boundary, and then vacancy clusters, number of vacancies grouped together, and then inclusions and precipitates. These are 3-dimensional defects, so that we have discussed earlier. So these are all defects. Here whatever we discussed all are defects. So other dislocations, that is, these are 1-dimensional defects: solute atoms, vacancies, grain boundaries, vacancy clusters, inclusions, precipitates, they are all defects. But there is another one which we did not discuss earlier. So that is called Nabarro stress. So Nabarro stress. So that is another obstacle. So this Nabarro stress opposes dislocation motion at atomic level. So we will see what is that at atomic level. As you know that others are also like vacancies, other dislocations or grain boundaries, they are also, probably you can think that it's kind of atomic level, but this is even at a smaller length scale. It's only one atomic distance. So pulse Nabarro stress is corresponds to only the displacement of or the barrier of only one atomic displacement. Okay. So pulse Nabarro stress is called at atomic level. It opposes the dislocation at atomic level because it involves the obstacle or barrier of, let us say, one atomic distance. So we will see what is that pulse Nabarro stress. So for To see the pulse Nabarro stress, so we need to understand that when the dislocation, I will write somewhere here, I hope it is clear, when one dislocation moves from one atomic one equilibrium atomic position to another, so it needs to cross an energy barrier, and that is called pulse Nabarro barrier. That is pulse Nabarro stress we need the dislocation need to overcome, and that is called pulse Nabarro barrier. So what is happening here is, let us say this is the extra half plane in this case, and then after some time, so what will happen, dislocation wants to go move towards right. So what will happen, after some time the extra half plane will move to this distance. But if you can see that, if you see the configuration, so it is not totally shifted to this position. In here you can see that from the this is we can call is a position, equilibrium position 1, and then this is position 2, and this is position 3. So the number 1 and number 3, number 1 I will write like this, number 1 and number 3, they are equilibrium position and they are stable. These are stable equilibrium. But if you see the number 2, this is a little different. This is unstable equilibrium. So why it is unstable equilibrium? Because if you see this, if you consider all these planes like this plane or this plane, so they are not at a stable position. Here if you see in a number 1 case, so these extra half plane is in between these two rows of atoms, and even in the, if you go to the third case also, these extra half plane, this extra half plane is in between these two rows of atoms. But in this case this is it's unstable, so this wants to go on the right side, and then what happens, these rows of atoms wants to align with this one. So that is why it is not a stable equilibrium. So what happen is that what will happen to the force with respect to distance. So we want to plot it now. So the applied force, or you can write like even applied stress in terms of applied stress. So and if you plot distance on x axis or abscissa, so what happen is this will look something like this. So position 1 will 1, position 3 will be here, position 2 will be here. So as you know, the force versus distance will give you energy. What will happen is the force required to move the dislocation will be tau Pn. So that is the stress required. So I would write here, so tau Pn will be the stress required to move the dislocation. Dislocation means dislocation on the above figure, dislocation without any additional help, and also means that there are no interaction from other dislocations or other defects without any external help is called the PN stress, that is PN or pulse Nabarro stress. So you can see here that's the barrier. That means it needs to have that much of force to cross the barrier, and so that from position 1 to position 3 it can move from one stable atomic position. So if I wrote here that one equilibrium atomic positions to another. So what happens when the dislocation moves on a slip plane? As we discussed that there are other defects, but there are several dislocations also will influence the movement of dislocation. Suppose this is a slip plane on which the dislocation moves. So we call it as a primary slip plane. There are some secondary slip planes also. We don't need to discuss much about it, but let us say there is a dislocation line. So this is a dislocation line, or we will simply call it dislocation, and dislocation is moving towards this direction, and then there can be some dislocations so these dislocations, I will tell what these dislocations are. These are called forest dislocations, and these dislocations are perpendicular to the plane of the slip plane. So you have this slip plane, sorry, this is dislocation line. So you have this slip plane, I am trying to thicken the line, so what direction the dislocation is moving is the slip direction. So and these dislocations are, the forest dislocations are perpendicular to the plane of the paper, whereas these other dislocations, these lines, as I told you earlier, this dislocation may not be a straight line, so it can be like a Maggi noodles. So so what happens is like these dislocation now which is on the slip plane. So this dislocation is moving, and I will write just moving dislocation here, and this is on the slip plane, and these are not on the slip plane. That means it is crossing the slip plane at some points. So what will happen now? So this dislocation will fail from will need to overcome these forest dislocations. So the forest dislocations are the barrier here or obstacle here for the moving dislocation, barrier for moving dislocation. A moving dislocation encounters periodic barriers of different spacing and different lengths. Spacings and different lengths. So there can be two types of barriers. So there are different types of obstacles or barriers. So first we can classify them as short range barriers or obstacles, and then another one is long range obstacles. If you plot them, force or stress is applied. If you plot them with distance, it will look something like this. So there can be a short range obstacle, and then long range obstacle will look something like this. This portion has a long range obstacle. So important to note that the short range obstacle, which are smaller and narrower barrier, that can be thermally activated. With the help of thermal energy, the dislocation can cross these barriers, and the other barriers, long range barriers, are it is called non-thermally activated. Or it is called as athermal barrier. So yeah, so I think we will discuss more on this in the next lecture. So we will continue this discussion, continue these discussions on dislocation dynamics, and we will discuss more about different mechanisms of dislocation movement. So we are here discussing the thermally activated the mechanism, and the other mechanisms we will discuss in the next lecture. Thank you.